is Muhammad Hamim Nur Hakim bin Shamsul. So the topic that will be discussed today is related rate and maximum and minimum problem.
Hi, my name is Rizal bin Rosli. I'm going to talk about maximum and minimum problems, also with related rates problems. In calculus, maximum and minimum problems involve in finding the highest or lowest values that the function can attain. These problems often require understanding the critical points of the zero function, where the first derivative equals zero or does not exist. For related rates problems, it's involved determining how different quantities change over time when they are related by some function. These problems typically use implicit differentiation to find the rate of change of one quantity given the rate of change to another.
Assalamualaikum and hello everyone, my name is Arif Hakimi and I will be showing you how to answer this question. Now first and foremost, I have provided you a simple concept on how to solve this question. First is what has been given, what do we need to find, and when something. So looking at the question here, it says that assume that spill from a ruptured tanker spreads in a circular pattern whose radius increases at a constant rate at 2 feet per second. So we stated here constant rate. So it means something over dt. Now, what do we need to put here? We put here radius. So we assume that it is dr. So we put here dr over dt equals to 2 feet per second. Now, what do we need to find? Looking back at the question, how fast is the area of the spill increasing when the radius of the spill is 60 feet? So we need to find the area. So we assume here dA over dt is what do we need to find. Now, when something, also looking back at the question, when radius of the spill is 60 feet, so we put here 60. Now, that is the first step. The next step is we need to differentiate. What do we need to differentiate? We differentiate the area. So the formula for the area is area equals to pi r squared. Now, why is it pi r squared? Because it is a circular pattern. Circular. And so we can continue to differentiate. So dA over dr equals to the power moved to the front and the power also minus 1. So the power moved to the front, it becomes 2 pi r. Now, that is not the final answer. Because why? The radius here, we need to substitute with 60. So 2 pi 60 multiply with 60. Now we got 120 pi. Now, we already found dA over dr. The third and final step is what do we actually need to find? Now, we need to find dA over dt. So we put here dA and we put here dt. And we fill both of the blanks with dr. We put here dr. Now, dA over dr we already found in the previous step, which is 120 pi. We multiply dr over dt, which has been given in the form in the question. So we put here 2. So we multiply both of this value. So we got 240 pi or 753.98. Now that is the final answer. But don't go just yet. We move on to the next question. Bye.
Okay guys, for the second problem, it states that a closed cylindrical can is to hold 1 liter, that is equivalent to 1000 cm3 of liquid. How should we choose the height and radius to minimize the amount of material needed to manufacture the can? Well, we know that for cylinder area, the formula is 2 pi r square plus 2 pi r h. That is our first formula right here. And for our cylinder volume, the formula is V is equal to pi r square h. That is for our second formula. So h is for height and r is for radius. So we can assume that V is equal to 1000 centimeter cube, because it says here 1000 centimeter cube. So we can substitute this amount into cylinder area volume, which is 1000 is equal to pi r square h, and we can make h as the subject, and we got 1000 over pi r square. This is our third formula. So we can substitute subs 3 to 1 because it has h right here. So our new formula is A is equal to 2 pi r square plus 2 pi r. So we got our h right here, 1000 over pi r square. And we simplify this equation into A is equal to 2 pi r square plus 2000 over r. Right. So to find the value for r, we need to derive this. So dA, to find value for r, is dA over dr is equal to 4. We substitute, we derive one by one, right? So 2 pi r square minus 1 minus with 2000 over r square. So with this we got 4 pi r minus 200 over r square. So we set the critical point into 0 because by using critical point we can find the minimum or maximum value. For in this case we need to find the minimum surface area value. So 4 pi r minus 2000 over r square is equal to 0, which we can substitute here this into here, which we got 4 pi r is equal to 2000 over r square. Now we substitute r square into here, which is we times it, we got 4 pi r 3 equal to 2000. Then we substitute this into here, which we then got r3 r cube over r cube equal to 2000 over 4 pi, which we then substitute cube into here, we got r 2000 4 over 4 pi. Then we can find our r, which is 5.42 cm. So we already got our r right here. We can substitute our r into the equation 3. So r into 3, right? So h is equal to 1000 over pi, which is our r right here, 5.42 square. H is equal to 10.84 cm. Thus we get our answer right here, r and h.
To conclude for the first questions, the rate at which the area of the spill is increasing when the radius is 60 feet is 240 pi square feet per second, which is approximately 753.98 square feet per second. For the second question, to minimize the material required to manufacture a closed cylindrical can with a volume of 1 liter, the radius should be approximately 5.42 cm and also the height should be approximately 10.84 cm.